All right, guys, this is a quick tutorial on how to do the homework tonight, and we're going to do relationships between energy, wavelength, and frequency. And these are really just mathematical relationships, and we have formulas for this, so it should be pretty straightforward. So I'm just going to kind of show you two waves. We'll call it A and B. Which one of these waves has higher energy? Hopefully you said B. And that's because if we have sort of, this is time, right? Over time, that wave is more frequent, right? And so more frequent means more energy. And so what we can say is energy and frequency, right? In other words, how many sort of beats per time are directly related. So you might have heard frequency as being the symbol F. Unfortunately, F kind of means other things in chemistry, so we tend to use the cursive V. So that's frequency. So energy and frequency are directly related. One goes up, the other goes up. What about wavelength? Okay, so that's where we go peak to peak, and we actually measure the distance between the peaks. So how does that correspond to energy, right? So the wave A has a bigger wavelength, but it has a smaller energy. And so we would say that those are not directly related. Those are, in fact, inversely related. So energy and wavelength, which the symbol for wavelength is lambda, are inversely related, meaning as one gets bigger, the other gets smaller. Okay? So energy to frequency are direct. Energy to wavelength are inverse. Okay? Which also means if we're going frequency to wavelength, what do we see? All right, if we come here, bigger wavelength, less frequent. So also inverse. Right? Inversely related. And so here are the equations on how we do this. The first one is going to be energy equals HV. Energy is E, V is frequency, H is called Planck's constant. And it is just that. It is a constant that is always the same. You will always be able to look that up. I will tell you what it is in a second. But that gives you Planck's constant. And so if you know energy, you plug it in. You know Planck's constant always, and you can solve for frequency, or the other way around, okay? Energy is usually measured in joules. V, frequency, is usually measured in per second, okay, per second. Okay, next formula is relating frequency and wavelength, and that is related by the letter C. C stands for the speed of light. And that is a constant. Light always has the same speed. We know that, so we can use that as our unit conversion. Frequency, we already said, was a unit of per second. Wavelength is a length, so this is in some form of meter, which should make sense because a speed is meter per second, right? Okay, so those are the two main formulas. So we've related energy to frequency and now frequency to wavelength. Can we get energy to wavelength? Well, yes, because both equations have frequency. So we can do substitution and plug in one for the other to get our final equation, which is energy equals hc over lambda. Energy, both constants together, lambda being wavelength. Okay, so those are the three formulas, and it just depends on what unit you're in and what unit you're solving for. So let's try one. So here we go. Here's your reference data. Here are the formulas. Speed of light is given here, which is 3.00 times 10 to the 8th meters per second. H is Planck's constant, which is given there, 6.626 times 10 to the negative 34 joules seconds. Joules times seconds, not per second. So let's do number one, and then you guys can try the rest. A certain photon of light has 422 nanometers of wavelength. What is the frequency of that light? So I know that my wavelength is 422 nanometers. and I want to know frequency. So which formula should we use? Well, the one that has wavelength and frequency. So I'm going to use that one. And I'm going to say that the speed of light equals wavelength times frequency, or x. What is the problem? Well, here's the problem. Nanometers, meters. You got to change one of them. It doesn't matter which one you do. Okay? So it's a whole lot easier to change the wavelength, I think. So I'm just going to literally, in the equation here, convert it to meters. And remember that there are 10 to the 9th nanometers in a meter. Right? So I just kind of do that and build it in. And then we're going to do this math out. Just grab my calculator. Here we go. So we're going to do 3 times 10 to the 8th divided by our new wavelength. There we go. And we should get frequency equals, how many sig figs do we want? Well, we got 3 for the speed of light. Remember, that's a speed. That's a measured value. And we got 3 for our wavelength. So I'm going to go with 3. So I'm going to say 7.11 times 10 to the positive 14th. And we need a unit. Meters cross out. We're left with seconds on the bottom. So 1 over seconds, which is good because that's the unit of frequency. So the frequency of this light is 7.11 times 10 to the 14 per second. Okay. Next one, and then we'll let you guys finish. What is the energy of a quantum of light from number 1? What is the energy? So 2 ways we can do that. We have this equation, and we have the energy to wavelength equation. It really doesn't matter which one you do. Energy equals HV. Energy equals H, which is a constant. Joules times seconds. Times my frequency. And if we do this right, our seconds cross out, and we're left with joules, which is great because we're solving for an energy. And then we just got to do the math and do our sig figs, which should still be 3 at this point. So we're going to go Planck's constant times our frequency. And then we should get 4.71 times 10 to the negative 19 joules. Okay, and that's our energy. All right, so hopefully that makes sense. Try the last 3 on your own, see if you can get a number, and we'll talk about it in class. All right.